Hello, good morning, good afternoon, good evening, everybody, wherever you might be. Today is my great honor and pleasure to welcome my friend and colleague and collaborator, Adam SIKORA from SUNY Buffalo. Once in Buffalo, I was taught, don't say sunny Buffalo, it's hardly ever sunny, it's SUNY. So SUNY Buffalo, from Niagara Falls, all the way from Niagara Falls, stated Skein Algebras and the geometric approach to quantum groups. Adam, the floor is yours. Take it away.
Thank you. Yes, as Piotr said, well, first of all, thank you very much. Thanks to Piotr and to all the organizers for inviting me today to this talk, to give this talk. And yes, I live in Buffalo, work at SUNY. Indeed, it's not sunny at all. Usually we have here instead of sunshine, we have cloud shine or snow shine. But Buffalo itself is near one of the wonders of the world, Niagara Falls, and you can see in the picture of it here. In any event, let me get to the matters at hand. So the plan for today is that I will introduce the theory of Skein algebras, which roughly one can think of them as two-dimensional quantum field theory. And then I will explain in what sense this theory generalizes and provide some kind of geometric intuition maybe to the theory of quantum groups. And I will discuss some other applications. This is a rich topic by now. So here is cloud of topics related to today's talk. Some of them we'll talk in a moment: knots, surfaces, three-dimensional manifolds, quantum groups, quantum invariants, character varieties, and some other topics I will not cover today, but are also related to what we do. So maybe I should point out, well, that as you can see here, conspicuously missing is noncommutative geometry. And so indeed, there will be plenty of noncommutative algebras with parameter Q. So perhaps you can call it a Q geometry, but we will not talk about C-star algebras. Although I am optimistic that that it's just a matter of time that connections, relations to noncommutative geometry will develop, meaningful connections will develop. All right, so with this many topics, interrelated topics, it's not that easy really to introduce this topic, the subject of today's talk, but perhaps we will try to do it. I will try to do it starting with knot theory, since also this is maybe the most elementary of the topics involved. So a knot in three-dimensional manifold is an embedding of a circle in it, and the link is an embedding of several circles in it. So in particular, a knot is a link of one component, and technically speaking, even empty set is a link of zero component. And we'll also use the notion of framed knots, which are embeddings not just of knots, but of annuli in them. And all those knots and links will be considered up to isotopy, which is homotopy within the space of embeddings. So now when a manifold is a thickened surface, so I here stands for an interval, then every link in M can be represented by its diagram in sigma. And classically, sigma is just R2, so then links are in R3. And maybe I can make just a quick historical comment that this classical knot theory started already in the middle of 19th century, because Lord Kelvin of the temperature scale, he conjectured that that atoms are like knotted tubes of ether, and chemical compounds are like links made of those knots. So, which is, I think, quite inspiring and interesting conjecture. Of course, the conjecture was turned out to be false, partially because nobody knew how to define the notion of ether, tubes of ether. But despite that, the interest in knot theory remained since then. And so usually knot theory, typically one is given two knots represented by diagrams. Here, by the way, are examples of knots and a hop link. And then the question is to determine whether those two knots are isotopic or not. And usually, if they are, then that can be confirmed by some trial and error, and which involves using, for example, Rademeister moves. So any two diagrams are related by sequence of these Rademeister moves. And sometimes it can be not that obvious at all. For example, this diagram turns out to be the diagram of the unknot. But in general, that's the easy part of knot theory. The harder part is proving that two diagrams, for example, the trefoil and the figure 8, represent different knots. Because then, I mean, we are not able to verify all possible isotopies, infinite number of possible isotopies between them. So this is usually done, proving that two knots are different is usually done using knot invariants. And so there are certain functions on link diagrams, at least in the context of sigma cross I, with values in some algebraic objects, and which are presented with the Meister moves. And so, for example, a simple example of that would be the number of components of L of a link. And another more sophisticated example is using algebraic topology, is the Alexander Polynomial, which is built using the methods of algebraic topology and was already discovered in the 1920s. And so then the progress in knot theory continued since then. However, the true breakthrough in knot theory, I think, came in 1984 with the arrival of the Jones polynomial. And in 1989, with Witten's interpretation of the Jones polynomial through Chern-Simons field theory. So maybe let me briefly mention Witten's approach to Jones polynomial through that theory. So in Chern-Simons field theory, one starts with a Lie group and with certain positive integer, and then given a link in a three-dimensional manifold M, there exists an invariant. Well, Witten postulates the existence of an invariant of that pair, and that invariance is given by certain path integral. And this path integral is over all connections on, well, I said on M, but actually I should set on some principal G bundle over M. And specifically, well, first of all, for each connection, one defines Chern-Simons functional or action by this integral over M. This will become a free form. And then one considers this expression. These are certain terms called Wilson loops related to components of L, and one integrates this over all connections, flat connections on this G bundle. And I'm not going to go into further details about this, especially that this is not really rigorous statement. Involves an integral over all connections, whose space is infinite dimensional. However, physicists are using integrals like that. They have their ways of computing and drawing consequences from integrals like that. So yes, this is just for a background, which I will mention a little bit later. However, a few years later, Zhitkin and Turayev constructed a rigorous theory of invariance of links based on the representation theory of quantum groups. And that theory takes as an input a semi-simple Lie algebra G, and it associates to links certain polynomials in variable q or fractional variable q, powers of variable q. So for example, for SLN, you get an invariant which satisfies these relations. So Zhitkin Turayev invariant of SLN for an unknot is just 1, and then it satisfies the Skein relation. What does it mean? Well, it means that if you have 3 rings which are identical everywhere, except for one ball, where in the first ball, the first link in this ball has this shape, has this tangle, the second link has this tangle, and the third one has this one, then those 3 links, where their values of the invariance are related by this relation. All right, and so for n equal 2, this invariant is the Jones polynomial of L, and this is invariant of unframed links, but frankly, it's more convenient to consider framed links, and I will consider a certain framed version of this invariant later in this talk. Yes, maybe to relate in this work to Witten's, let me say that actually Zhitkin Turayev did more than just that. In fact, they defined for every Lie algebra, say over complex numbers, and every K, a certain topological quantum field theory, which associates to each surface a vector space, and to each link in a manifold M, a manifold which has boundary this surface, well, it associates certain vector in this vector space called state space of the theory. And so in particular, if the manifold is closed, then it associates certain scalar, because this vector space for the empty set is just the field of complex numbers. And that scalar at level K is the invariant which I mentioned here at kth root of unit, or k plus second root of unit. All right, so now it will be useful for us to go further into the construction of Zhitkin Turayev. If I'm going too fast, or if you have questions, please let me know. So we will want to consider
maybe one simple question.
Yeah.
We think about vector spaces as observables. on a surface? Or?
Yes. Yes.
Okay.
Yes, thank you. So yes, you're right. Of course, they are not. It is not state space. It's a space of observables. Yes.
I see. Thank you.
All right. So we will want to consider in this talk not just links, but in general tangles in manifolds, which are just proper embeddings of compact one-dimensional submanifolds of M. So unions of loops and arcs have endpoints and the boundary of M. And we want to generalize the construction of Skein-Turayev tangles. And this was indeed done already for tangles in a cube by Skein-Turayev. And so more generally, they consider not just tangles, they considered ribbon graphs. So here's an example of a ribbon graph. As you can see, it's first of all, it is a framed graph. So it's a collection of, you can say, long rectangles with connected by vertices, but actually vertices are those coupons, so those rectangular, have this rectangular shape, and then framed looped components are also allowed here. And all right, so Skein-Turayev defined invariants of those under isotopy for any semi-simple Lie algebra, and they did it by considering certain Q deformations of the enveloping of the universal enveloping algebra of G. That Q deformation, denoted like that, it's an algebra over a field of rational functions in Q. It's a Hopf algebra, deforming the Hopf algebra structure of the enveloping algebra, and it's called the quantum group. And so the reconstruction involves the representation category of quantum groups, particularly finite dimensional representations. And this category has a rich algebraic structure, which whose details are maybe I will not discuss here, but this algebraic structure is makes it into a so-called ribbon category. And then it turns out that you can label any ribbon graph by representations of the quantum group, like I did here, and you can label the graph, a graph like that. You can label the coupons of it by so-called intertwiners. What are intertwiners? Where there are morphisms in this category between tensor products of representations, like for example, this coupon is labeled by intertwiner, which is a morphism of this form, because V3 and V1 are on the bottom of it, and V4 and V5 are on top of it, and star means the dual representation, and it's related to the fact that V1 is coming down rather than going up. So once you do this labeling, the Skein-Turayev machinery or theory defines a morphism in the category of representations. And in this case, this morphism goes from V2 tensor V1 star dual of V1 to V3.
Sorry, may I have a question again?
Yes.
So regarding this ribbon category, usually the category of representation, for example, representations of a group form the so-called Tanakian category. This notion of ribbon category is somehow related to this Tanakian formalis, or is it completely different story?
you know, I remember something about Tanakian duality, if anything. I don't remember Tanakian category. And I don't
The
think...
main notion is the notion of the fiber functor in this Tanakian formalism. So
yeah, I
so
don't
Adam,
think...
so Adam and Adam, yes, it is Tanakian category, but it has it's finite and has extra structure.
so Tanakian plus something, yes?
Yes.
All right,
Okay.
very good, thank you.
It's not semi-simple, actually, on top of it.
Mhm.
It is
Oh, okay.
Tanakian, but it's not semi-simple.
Yeah, all right.
Now, since there are already questions, let me also ask mine. Could you, Adam, Adam the speaker, not Adam the question asker, tell me again what you mean by these, you call them coupons, these rectangles that clip on together two ribbons?
Well, I'm not sure what else to say. They are just little rectangles attached at the ends of the edges, like the way you see it here. You know, so there are fancy versions of vertices of the graph. But the point is that maybe to make it more meaningful, this theory wouldn't work for simple vertices. So you need to have, those vertices have to be decorated by certain intertwiners, and intertwiners are morphisms. Like I think it's very hard. It would be hard for me to do all full proper definitions. So I was hoping I can explain this in this example. So, you know, we are thinking of this morphism as going from the bottom to the top. It's a matter of convention.
Yeah.
We start with V2 tensor V1 star, because V1 star goes down instead of up. And here, the input for F is going to be V3 star, V1 star on the bottom, and the output is V4 star and V5 star. V5 star, yes. And we have to decorate it by a morphism.
And you always have two inputs. No, sorry. You can have one input and two outputs, right? What are the rules? Can you have more than
here
two?
You see two inputs and one output. In general, you can have arbitrary number of inputs and arbitrary number of outputs.
Okay. And what is the word you use to describe them? Yeah, I understood coupons, but it doesn't make sense to me.
Coupons.
Coupons.
Yes.
Really? Okay.
Like, yes, except that there's no discount pricing on them. They are decorated by intertwiners.
Okay. Okay. Fine. Thank you.
It's a terminology coined by, well, at least maybe by Zhodkin-Turayev, if not earlier. Okay. Yeah, the point is that in this construction actually can be done for any ribbon category, but in particular, the particular useful one is done by representations of the quantum group UQ of G. So this gives an invariant of tangles in a three-dimensional cube. But we want more general construction. And so for that, I will consider, let us consider a notion of a Mark-free manifold, three-dimensional. So free manifold means three-dimensional manifold. It's always oriented, that manifold. And that means M, the manifold, together with certain collection of oriented intervals in the boundary of it called markings, which can be empty. Well, if the boundary is empty, then N is empty, but N can be empty even though boundary is not. And then it turns out that to make our theory meaningful, we'll consider not only tangles in M with endpoints in N, but more general class of graphs called N-webs. So this is an example of a free web. It has framing, which I didn't picture here. So usually when framing is not shown, it is parallel to, well, used to be called blackboard framing. but maybe we don't have many blackboards left. Then there were whiteboards. Now we have computer screens. So the framing is parallel to the computer screen. And so it has external, well, it has ends. The ends must lie in this calligraphic N, in those boundary arcs. And then it has internal vertices. They're all n-valent, and they're either sources like this one or sinks like this one. And it may also have loops. All of those edges and loops are oriented. And the vertices are rigid. So there are also little disks with edges coming out of them. All right, I know it can be a little bit complicated, but hopefully we manage. So we will think of the marking as coming towards us, perpendicular to the screen. And so here is a picture of those ribbons ending at the marking, red marking. And then we need the diagrammatic presentation of such a graph. And so we will project them on the screen, and we will project it either this way, with arrow indicating that the red marking is the closest to us, or this way, arrow indicating again that the red marking is the closest to us. So even though sinks and sources seem unnecessary from the point of view of knot theory, they actually turn out to be we actually needed to make the theory reasonable for our purposes. And I will maybe elaborate this in a moment more. So yeah, basically the reason we introduce those sinks and sources because they will make the theory more manageable, even though they add some initial complication to the theory. All right, so now let's fix a ring of coefficients R with certain fixed invertible element V. And we are going to use the traditional letter Q, which is V to power 2n. So in other words, we are going to use fractional powers of Q. And then with this ring of coefficients, we can define the SLN Skein model, or maybe I should have said stated SLN Skein model of the mark manifold M, N. And it's a R model. It's R model, which is built of all n webs in the mark manifold. So you consider linear combinations of such webs, and then you quotient this huge infinite dimensional free model by certain Skein relations.
Adam, can you remind me what R is?
R is here. It's a ring of coefficients. We just make sure that it contains this variable Q in it.
Yeah, but arbitrary, I mean, commutative ring, non-commutative.
Commutative. Yes. A commutative ring of coefficients with fixed variable. Okay. Fixed invertible element. All right. So what are the Skein relations? Well, the Skein relations are inspired by the relations between tangles given by the Reshetkiv-Torayev construction. All right, so first of all, imagine that you have three webs, and they're identical everywhere except for one ball. When the first web looks like this one, second like this one, and the third one like this one, then the Reshetkin-Torayev invariants of them are related by this equation. And we are making now this equation, into a relation in the Skein model for any Skein related webs like that. Now you can see the coefficients in this relation changed because now we are considered framed links, not only links, but n-webs. And in particular, a loop like this, well, a kink like that is not the same as just a straight arc, because this kink introduces framing, but it's related to the straight arc by this multiplicative coefficient. And then the third relation says that if you have empty loop, sorry, trivial loop in M, then can be eliminated, and its value is given by this quantum integer with a special sign. So these are really relations satisfied by the quantum SLN invariant of Reshetkine-Turaev in its framed version. And then maybe the third one is, the last one is the most interesting one, or the most difficult one. It says that you can bring a sink and a source together, and you can resolve them by considering all possible positive permutations or positive braids representing all possible permutations. And so this will be equal to a sum of all such positive braids with these coefficients, where L of sigma denotes the length of permutation. All right, so as I said, the motivation for that is that the Reshetkine-Turaev functor or construction on tangles in a cube will satisfy these relations. Well, maybe I can make, okay, so to explain this further, well, as you remember, Reshetkine-Turaev construction involves coupons, graphs with coupons. So this vertex here of the source actually is a tiny coupon, and that coupon is labeled by an intertwiner, and that intertwiner is the anti-symmetrizer. So it's one in the complex numbers, which are isomorphic to the highest external power of Cn, which lies in the tensor power of Cn. And Cn here is considered well, okay, so this should be perhaps not C because it should be C. It should be really C or CQ. Okay, let me add here Q. All right, and so this is the fundamental, this is the defining representation of the quantum group UQ-SLN. So remember, each coupon must be an appropriate intertwiner. So I define the appropriate intertwiner for, well, to be specific, I defined proper intertwiner for this sink. And the dual of it is the intertwiner for the source. And then let me make maybe a more technical comment here. The comment is that in the Reshetkine-Turaev theory, in general, a coupon like that is not the same as coupon as that, but we modify the ribbon structure on this category to make this equality possible, and this modification introduced those signs which otherwise wouldn't be there. But that makes the theory simpler because now we can rotate edges like that around sinks or sources. All right. So those relations, by the way.
Can I ask, out of curiosity,
yeah.
Any place where you need Q to be root of unity?
No.
At the moment, yeah, just
yeah. The whole
idea
theory
just
actually,
working in Novikov ring, right?
Yes.
So that's all, right? Yeah.
Yeah. Good. Thank you. Yes, so maybe actually I should, maybe this was a good comment or question because I should be more careful here. So I started with any arbitrary ring R, and then I really should consider this quantum group over this ring. So really what I will do here is consider a Lusztig version of quantum group, which allows to be defined for any over any ring R. All right, so those relations were already considered, or Skein model based on those relations was already considered by me, I guess over 15 years ago, almost 20 years ago, in fact. I will come back to the meaning of those relations and purpose of those relations in a moment. However, we have more relations near boundary of M. And so we have this relation, which allows to resolve all crossings, all vertices near a boundary. And here, empty circle means either arrows to the right or arrows to the left. So this means two relations with arrows to the right and arrows to the left. And then we have also this relation, which allows to eliminate little caps like that. And this relation allows to resolve caps of other sort. And then there's a way to eliminate crossings near the boundary. And here A and C are certain powers of Q, which are not essential. The details are not essential here. And this relation, in fact, is not necessary if quantum integer n-2 is invertible. All right, so for n equal 2, this Skein model is equivalent to the Kaufman bracket Skein model, first considered without boundary points by Przydycki to Rayev, and then with boundary relations by Tangle. And I should mention also that for n equal 3, this construction was already done recently by Higgins and also by Froman and myself. A version of it, at least, was done by Froman and myself. All right. So if you are still listening, maybe by now we survived the hardest part of the talk, this technical definition of a Skein model. And
Adam, sorry, because I'm listening and watching. Can you explain to me this symbol?
Oh, this symbol, this is Kronecker delta, and it means it's 1 or 0. It's 1.
Yeah, but you have j less than I, which means what? If j is bigger or equal than I, then it's 0, right?
Correct, yes.
Okay.
Yes, good. Thank you for pointing it out. Indeed, I didn't define this. All right, so now I think seeing this very complicated definition, it's natural to ask, why? Why do we care? Why should you care? So let me talk about that. And first of all, let's consider a situation when there is no points on the boundary. So and that Q is equal to 1. And if I go back here to Q equal 1, then you will see that this term disappears, and it says that this crossing is equal to that crossing. And that means that we can define a product of webs in the manifold by taking a disjoint union of them, any disjoint union of them, because any two disjoint unions of them will be related by passing the strings one through the other. All right, and we kind of lose the not Fiore aspect of this construction, but so be it. So what we have is that this becomes a commutative algebra over R, and it's reasonable to ask, what's that? And so here it's we need to change gears to explain that, and I need to introduce character varieties. So maybe to motivate character varieties, let me start by saying that as as many of you know, there is no algorithm to distinguish two groups given by generators and relators and relations. This was already proven by Novikov in the 50s, I think, or 60s. And so one often distinguishes groups by representing them in some other matrix group. So in other words, one considers a space of all representations, denoted here by home. And it's natural to identify conjugate representations. So G acts by conjugation on those representations. And so it's natural to take a quotient, and such quotient is called the G character variety of gamma. And for a reductive group in GLNC, for matrix group with coefficients in closed field, this quotient has naturally a structure of an algebraic set. And maybe I can explain this in an example because it's not intuitive. So let's say we take the free group on two generators and study representations of it into SL2C. Then up to conjugacy, it turns out that they are determined by three values: a trace of row of A, trace of row of B, and trace of row of AB. And yes, so maybe I can admit here that I am lying here slightly. This is actually not just a traditional set theoretic quotient. It's a quotient in the sense of geometric invariant theory or categorical quotient. And but that's a technical detail. And so in particular, given the statement which I just made here, all representations into SL2C can be characterized by three complex numbers. Okay, so the character variety is just C, is just a affine space of dimension 3. What about Z2, Z square, which is the free abelian group on two generators? Well, then the character variety will be subset of that. In fact, if we denote those traces here by tau A, tau B, and tau AB, they will always satisfy this polynomial identity. And it turns out that any point, any triple of taus like this, satisfying this identity, corresponds to a unique representation of Z cross Z. So this is the character variety of Z cross Z. And then in algebraic geometry, of course, once you have algebraic set, you can talk dually about the coordinate ring of it. And so this is the coordinate ring, and taus are functions in it, are functions on the variety, and they're called trace functions. Now, character varieties are very important in geometry because they classify various geometric object structures like hyperbolic structures or projective structures, say on surfaces and higher dimensional manifolds. They also parameterize flat connections, in principle, G bundles over M, and as such are important in physics. And so going back to the discussion of Witten approach to quantum invariance, well, maybe I can leave it on the cliffhanger like this and just tell you, first of all, explain to you guys what the Skein algebra is for Q equal 1. Well, this algebra for Q equal 1 turns out to be the coordinate ring of the character variety of M. So when I say that, I mean, of course, that we should put here the fundamental group of M. Okay, so even in this very trivial case, when Q is equal 1, when most relations, several relations just trivialize, you get something non-trivial. You get description of the SLN character variety of the fundamental group of the manifold. And that isomorphism, by the way, requires a choice of a spin structure for M. at least for n equal even. And knots here, roughly speaking, knots in the Skein module are roughly speaking corresponding to the trace functions tau gamma for gamma representing the homotopy type of the knot, homotopy class of the knot in the fundamental group. So
Adam, hi.
we'll see.
Adam,
Yeah.
it's Ludwig. Hi, Ludwig Dabrowski. Hi. Can you just shed more light a little bit about how spinors come here? So this would be kind of representations of pi1 of m into SLN, right? That's what you say here. That's right. Modulo this conjugacy, which you said. Like that.
Yes, this is on the right side. You ask me to shed more light on
Why
what?
spin structure should be present on manifold M?
Well, okay, so if every three-dimensional manifold has a spin structure, because it has trivial tangent bundle. Now, why do we need spin structure? It's actually very involved. So there's unfortunately, well, yeah. So unfortunately, when I say that a knot is represented by conjugacy class, well, the knot corresponds to tau gamma. Actually, this is not entirely true. It actually corresponds to plus minus that, and the sign to set up to fix the sign will need spin structure. But that's a kind of technical topic, detail which I'm not sure I can really elaborate here.
Okay.
So what does it really mean, by the way? Well, it means that you can forget about these relations. Yes, those relations become trivial for Q equal 1. You can consider n webs in manifold with the relation saying that a synchronous source like that is equal, it's certain signed sum of tangles like that. And it turns out that this gives you that this kind of Skein module is an algebra, it's a commutative algebra. And it turns out this commutative algebra describes SLN character variety is the coordinate ring of the SLN character variety of M. Yeah, the result is quite, I guess, non-intuitive, and I don't claim it's trivial, certainly. But I want to say that I want to connect it now to what I said earlier. And so what is then a Skein module of M? At least when the boundary of M is empty or when there is no endpoints on the boundary, well, you can think of it for arbitrary Q some sort of Q deformation of the character variety of M. Okay, and this is related to what I said earlier about Witten's work, because Witten said that quantum invariants are given by certain path integrals with the Chern-Simons action, and the biggest contribution to this path integral should be given by connections with the extremal value of the Chern-Simons action, and those are precisely the flat connections, and flat connections form character variety, and so the path integral somehow should describe quantization of the character variety. All right. So that's the first good thing about this construction. But now to develop this theory further, let me talk about special type of three-dimensional manifold of the form surface times interval, where the theory will be much richer. And so if you have a surface sigma and a finite set of points on the boundary of it, and that is called a marked surface. And then if you multiply it by an interval, you get a marked free manifold, because those become markings, arcs in the boundary of this three-dimensional manifold. And now, even when Q is not 1, this Skein module is an algebra. And this algebra, because given two webs, alpha and beta, you can stack alpha on top of beta or beta on top of alpha. and that's well defined. And unlike in arbitrary free manifold, when there's no notion, the problem in arbitrary free manifold is that there's no notion of up and down. There's no notion of putting something on top of something else. But in this three-dimensional manifold, you can do it. And it will be convenient, instead of talking about surfaces with specified boundary points, it will be convenient to remove a complementary set of points, B prime, from the boundary, such that each point of B, each of the marked points or base points, is separated by points of B prime, like in this picture. I know this may be a little bit technical, but bear with me, and also maybe it's not really as important because it's just bookkeeping, so maybe it's not as important for us right here. But anyways, the marking is always perpendicular to the screen, standing on top of B. And now, with this convention, once we remove points of B prime, we can project the endpoints on this interval here. And we'll use arrow, like we did before, to indicate the original height of the endpoints. All right. So from now on, we will just talk about Skein algebra of a surface with certain ideal points in the boundary instead of Skein algebra of this marked surface. Again, this is just bookkeeping, so don't worry too much about that.
Adam, forgive me a stupid question about bookkeeping, but could you remind me, please, this n counts what? This natural number n?
N is the index in SLN. So that's a fixed number, fixed natural number, which we consider here. And n, of course, will appear in the definition of this construction. So here you have n webs, which means all the vertices are n-valent, and n appears in the coefficients. But this is a theory corresponding to SLN or to UQ-SLN.
But purely in terms of not theory, this n counts what? The valence of sources and
yeah, you can say that, yes.
Okay.
Well, from the point of view of not theory, of course, when you have a knot, the knot doesn't have any n in it.
That's why I'm asking this question, yes.
Yes. Maybe actually, this is a good question, and maybe I should connect this better to knot theory. So let me do it right here. So what's an immediate, maybe, reason for this construction? The most naive reason for this construction is this. Any link is a web, it's an n web, which happens to have 0 sinks and sources. And therefore, it can be thought, it represents an element in the Skein module. All right, so we can consider here its class in the Skein module. Let me do it in the proper way. So this is not true just for links, but it's considered true also for tangles. And so it's a topological invariant of links up to isotopy in the marked manifold. And it's meaningful as long as you can compute the Skein module of that. What does it mean, compute it? Well, for example, if you are able, if it's a free R module and you can find its basis, then generally speaking, it's not difficult to represent any link in the basis, and then you have some concrete invariant of links in a manifold. So this is like maybe the original motivation for constructing Skein modules. By now, frankly, we don't really use those Skein modules to really do that. But Skein modules themselves have a rich theory, which we're interested in. But yeah, as I said, that's the original motivation for Skein modules.
Okay, thanks.
All right. So let me talk about the next property of Skein modules. And I will do it just for the thickened surfaces, but it's true in general. So take any surface and take an arc connecting ideal points of the surface. And then you can cut the surface along that arc. You get new surface, sigma prime, which may be connected or disconnected. And I claim that this operation defines a homomorphism, algebra homomorphism, from Skein algebra of sigma to Skein algebra of sigma prime. And the way it works is once you do the cutting, you get once you cut a web, you get a web which is only partially stated. It's not stated on those new edges created by cutting along C. And so you state them in all possible ways. The member states are numbers from 1 to n. You consider all possible ways to state them. And the sum is the value of this homomorphism. By the way, it's very unfortunate I said it's n, because actually it should be k. This is unrelated to n, which you see here. And so this splitting theorem was proved already by Tangle, by my collaborator, for n equal 2, and by Higgins for n equal 3. And it's very useful because it allows to analyze Skein algebras through its pieces. All right, so now let's talk about simple computations. Well, actually, the computations are not simple, but computations of Skein algebras for simple surfaces. And so let's take a monogon. So it's a disk with one boundary point missing. And it turns out the Skein algebra of it is just the ring of coefficient R. And that shouldn't be surprising, because if I put any web in it, I can use boundary Skein relations to remove, to simplify everything which is inside. And so this is the ring of coefficients R. Now let's consider a bigon. So bigon is a disk with two ideal points, which are removed from the boundary. First of all, what's the product of webs in bigon? Well, every web will look something like that. And I drew here one edge, but this is of course symbolic. This can be several edges with, so several states will be here used, like what I did here. And then when you take a product, well, graphically the product will become given by x on top of y like that. All right, and so it turns out that this is an algebra which is generated by simple arcs like that. And they have, of course, two indices, I and j, which are any number from 1 to n. So the Skein algebra of a bigon, well, okay, let's take an arc which cuts bigon into vertical arc like this. And by the splitting theorem, which we just discussed, this arc will define a homomorphism from Skein algebra into tensor product of Skein algebras of its pieces. But each of the pieces here is again bigon. So you have, it defines homomorphism like that. So we claim that a Skein algebra of the bigon with this operation can be made into Hopf algebra. All right, and for Hopf algebra, I need to tell you the value of the co-unit. So because those are generators of the algebra, it's enough to define the co-unit on the generators, and the generators is just the Kronecker delta ij. And what else we need is, well, we need the antipode. And the antipode is given essentially by 180-degree rotation of a web, like what you see here. And this rotation is also involves conjugating the states. So you replace I by n plus 1 minus I. This is involution on the states. And then there is certain power of q needed to normalize it. So C's are certain powers of Q, which I defined earlier, but actually they're here. But that's not really, the details of that are not really essential. In any case, it turns out that this is a Hopf algebra. And so you can ask, what kind of Hopf algebra is that? So Thangler and I proved that this is the quantized coordinate ring of SLN of them.
Sorry, Adam, could you please clarify one thing? Sorry to interrupt you.
Yes.
This M, when you have this product refers only to coefficients. So this M runs what set? You have a product over M. M is a running index. It runs what set? It varies from where to where?
Oh,
yes. Here.
Okay. All right. Very good. Very good. Well, I know. Well, okay. What? Good eye. Good eye. All right. Very good. So, well, I see. I wrote it in this way because, frankly, it's a product of C's indexed by these J's and product of C's indexed by these I's. And frankly, well, you consider all J's here and all I's here, and there may be different numbers of them. So this symbolically makes sense, but I on purpose didn't specify. Maybe I should be, so, okay. Product M. This will be better, I think. Okay, and now one is from 1 to L and another is 1 to K.
All right, that's exactly what I.
Yeah, very
thank
good.
you so much. Yep.
Very good eye. I finished preparing this talk. What, it was 6 a.m. in the morning, my time. So I apologize for some typos, and also I should also mention, maybe this is a good point to mention, good time to mention that, as you have seen, there's many facets of this theory, and I'm trying to mention different people who did work and contribute to this theory, and I apologize to them if I forgot. All right, so this, and frankly, I know this is not the best notation really, because this should be really the group SLN. This is the quantized coordinate ring algebra of SLN, of a group SLN, but I would just note it this way. In any event, is the dual Hopf algebra to the quantum group UQ SLN. All right, and this result was known already for n equal 2 and n equal 3 by Constantinole and by Higgins. However, our generalization is quite not trivial here. It's harder to do it for n more than 3 for reasons which I will explain soon.
Adam, can I ask?
Yes.
Why don't you put capital S, capital N? So I think O means the coordinate on SLN.
Well, that's right. But so it's a Q deformation
of SLN, of coordinates on SLN.
Yeah, Ludwig is right. I mean, here, at this point.
Yes. Yeah. So I agree. This is not the best notation, but
Okay.
let us just live with it. It's a Q deformation.
That's why people sometimes, like you call quantum groups, that's what is deformation of Lie algebra. Universal developing algebra of deformation. And
That's right.
C-star algebra is called quantum group functions on SLN or coordinate ring.
I see. So you don't like calling this a quantum group?
No, because it's in fact the quantum universal developing. This is more like a quantum Lie algebra, not the quantum group.
No.
Wait.
UQSLN would be the formation of enveloping.
Oh yeah. So
algebra
that's
of SLN.
this is a quantum group. All right. Yes, but this
It's
is more like a quantum.
Okay, but that's just
I see.
naming. Okay.
I see.
Sorry. So probably it's a typo. Instead of small SLN, it should be capital SL.
Yeah, that's what
Yes,
we are
yes,
saying
that's-
here. Here, it should be capital SL.
Yeah, that's what I just.
Also, L
that's what
should
we
be
discussed.
capital.
Yes, that's what we discussed, and that's what I already mentioned here. Yes,
Mhm.
and then somehow aesthetically I prefer. So, but I will be using later on this symbol, so I hope you guys forget me.
Of course.
Especially it's a just dual objects you can say to this algebra.
Yeah.
And
But I'm sorry, may I ask? I do have a question. So you
Yes.
write product over m's, right?
Mhm.
yes,
So there has to be finite number of m's where everything is non-zero. Or what?
well, you take product over those indices. So for each of those indices, you take C with that index and you take their product. So this is product of L, this has L factors, and this has K factors.
And they're always non-zero because this is just powers of
Yeah,
two.
that's not the question. No. My question is why is it finite? Okay,
Why is what finite? Sorry.
these products are finite.
Why
So
products are finite?
is that where you start using root of unity thing? So you have finite domain representations.
But I'm not. But product is finite. Well, so a product of two webs. So every element is a linear combination of webs, which are geometric objects. A product of two webs in a bigon, for example, is given here.
Yeah, sure. But now you're looking at the coproduct, right? It's a
Yes,
question of coproduct, not product, coproduct.
Yes.
Right.
So let's go back to the previous one. So if you have a web which has, if you have a web which intersects C at one point,
Yep.
coproduct is given by sum of n terms. If it intersects C in 2 points, this sum has n squared terms because you consider all possible statings on two ends.
Yeah, but you pick up some intertwiners, right?
Sorry.
So you choose kind of intertwiners between your i's and I bars. So if I can see correctly.
There is no intertwiners here. You just consider all possible states. So if you consider some sort of web, imagine any graph or link, just for simplicity. If you cut it, well, it has some number of endpoints at C. You know, if it has 2 endpoints, now they will be unstated. So you consider all possible statings of them. For 2 endpoints, there's
So then, okay, why are there finitely many i's? Maybe yes, you have I1 to In. So you are summing up over i's, right?
Yes.
Why are there finitely many of those?
But those i's are just numbers, positive
What are they?
numbers. And a terrible mistake is that this n is really unrelated to our n. Some should be k.
Yeah, sure. Forget that one, right? Yeah. No, but what are these i's? Because I got some kind of lost
Numbers
somewhere.
between 1 and n, because webs are stated by numbers between 1 and n. So endpoints are labeled by numbers between 1 and n.
Okay, so you're not doing representations. Okay.
Yep. And all right, so what this result gives us is a geometric interpretation of quantum group, a novel geometric interpretation of a quantum group, and which turns out gives some intuition to new intuition and simplification to old notions. But before we get there, let me first say this, that now let's take any surface with an ideal arc in the boundary. This is this arc. Then we can carve a bigon along that arc. And so it will define a splitting like that. And if you remember, a cutting along the boundary of this bigon will define a homomorphism like that. It turns out that this homomorphism makes Skein algebra of sigma into a comodule, right comodule, over the Skein algebra of the bigon, which is the quantum group. Or at least the Hopf algebra or QSLN. All right, and then if you are not comfortable with comodal structures, well, by duality, any right comodal will become is a left UQ module. So these Skein algebras are left UQ modules. Well, and in fact, any boundary arc will determine the structure. Now, let's imagine an ideal triangle in surface sigma. And this ideal triangle is pictured here. Let's see if I can make it larger. And so then sigma minus the triangle, let's say it's a union of two different surfaces, like here, because these are ideal points. So this triangle splits surface into two parts. And then I claim that there is a homomorphism from the tensor product of Skein algebras of the two pieces into Skein algebra of sigma. And the way it works is that if you have one skein, a skein means a linear combination of webs, and another one like that. So this edge represents many edges, possibly, of course. Then you can extend them continuously down to this edge of the bottom edge of the triangle. So you have this operation. And you can ask, is this an algebra homomorphism? So, you know, all those three S's here are algebras. This is tensor product of algebras, or it's also an algebra. Is this an algebra operation? It turns out that it's an isomorphism of modules, but not an algebra operation. And to make it an algebra operation, we need to consider the notion of a braided tensor product, which was developed by Majid. And then we have an isomorphism. And so this gives this picture gives some geometric interpretation of theory of braided tensor products, which I think abstractly, algebraically, it's a very complicated, very technical theory. So let me give you some more concrete application of that, or example of that, to the notion of transmutations of quantum groups. So this is a quite general notion, also considered by Majid. It's very much related to what I just said. So let's take any Hopf algebra H.
Sorry, Adam, could we come back to the previous page?
Yes.
The meaning of this theorem. So if you think about this braided tensor product, then you mean an algebra structure.
Yes.
And then the isomorphism in this theorem is an isomorphism between algebras. Then.
Yes.
So the only difference is that this is not a tensor product of algebras with slot-wise multiplication. There is some braiding between the generators, but
yes,
whenever you have this braided algebra structure on this tensor product, it is an algebra isomorphism.
Correct.
Mm-hmm. Okay.
Yes. Yes, as a module, it is just tensor product, but the algebra structure is deformed. And so this next example explains this in a more concrete way. So let's actually introduce this concept very generally. Let's take any Hopf algebra, and such Hopf algebra, any Hopf algebra will have an adjoint action of it on itself. And how does it work? Well, adjoint action of little h on little g is given by this formula. So here I'm using Swidler's notation. H1, H2 are, they come from the coproduct on H. This is the antipode. And it turns out that it makes H into an H module algebra. And then you can consider multiplication on H, which is a bilinear map, of course. And in this multiplication is equivariant with respect to the adjoint action. However, the co-multiplication is not. So then Majid defines a certain deformation of the co-multiplication for which this map is equivariant under the joint action. And it's called transmutation, I think. And well, you can consider this dually. So you can consider left adjoint coaction on H. And this coadjoint action now will be given, it will go from H to H cross H. It will be given by this operation. It makes H into H commodule algebra, but not a H commodule algebra. So to make it into algebra, Majid studied this topic quite thoroughly. He wrote a book about this, about the braided products and those transmutations. And so he proved this theorem that this modification of the product gives a commodule algebra structure under the coadjoint action. And of course, this is quite abstract. The proof is very difficult, but this has very simple interpretation in our theory. So let's consider a punctured monogon. This is a punctured monogon. And I claim that as a module, it is isomorphic to the bigon. And the isomorphism is given geometrically like that. You can embed any web and is in the bigon into punctured monogon like that. And so as vector spaces, they are isomorphic, or as model, they are isomorphic, but this one has modified multiplicative structure. And I claim that this complicated formula describes the multiplicative structure of the punctured monogon. And actually, proof of this theorem is quite easy. It's geometric and actually is very simple with this geometric interpretation. Another application of this theory to quantum groups. So the quantized coordinate ring of SLN has a co-R matrix, which has a certain bilinear form on it. And this bilinear form is dual to the R matrix, and it allows to make this the category of modules over this algebra braided. So it turns out that this pairing, which often is given also by some complicated formulas in literature, has very simple geometric interpretation. Basically, if you have two webs or two skeins like that, you put them together like this, and you take. So okay, so here, this picture actually represents a bigon the same way as this picture represents a bigon, where I open the top and bottom of the ideal point, and you just put them together like this, and you apply the counit to that, and you get the pairing.
Adam, just very simple bookkeeping questions. What do you mean by comodule coalgebra? What's the difference between a comodule and comodule coalgebra? Because you also have a coalgebra structure on H. Sorry, of course, sorry. Yes, that's okay. And here I understand that you also mean Sweetler notation in your formula.
Yes, yes, this is Sweetler. Yes.
Here, right?
Yeah. Yes, this is Sweetler notation. Oh, I see what you mean. Yes, thank you. Yes.
Mm-hmm.
All right, moving on. So an important question in this theory is finding basis of Skein modules. And this is not, even the version with Q equal 1, which reduces to study of character varieties, even in the context of character varieties, it is important to find basis of those coordinate rings. Basis as vector spaces. And in general, it's an open problem. It's an important subject of something called Fogg-Goncharov theory. They have certain conjectural statements about what the basis should be. These conjectural statements use tropical geometry and some other fancy machinery. In any case, for n equal 2 and 3, the basis of Skein algebras are known. and in particular also of the character varieties. And they can be found using the method of confluence, which I developed with Bruce Westbury a while ago. However, that method fails for n greater than 3. And so this goes back to what I mentioned before, that actually proving this isomorphism is much harder for n greater than 3 because we don't really have a basis a priori of this algebra. However, of course, now, given the isomorphism, we have a basis because we have those quantum groups, or whatever you want to call them, the formations of the coordinate rings, have so-called famous, well, Kashiwara-Lusztig canonical basis or crystal basis. So Skein algebra of a bigon has a basis, Kashiwara-Lusztig basis. And now let's consider a triangle. Where is my triangle? Oh, my triangle is not here. All right, there will be a triangle. So let's consider a triangle. We can compute the Skein algebra, the basis of the Skein algebra of a triangle using the statement before. And I claim it's a tensor product of two of those quantum groups. And the reason is, yes, if you go here, you can close this picture on the right. You can close those arcs into a bigon, and you can close those arcs into bigon. And you have two bigons with a triangle, which together give you a triangle. All right, so the Skein algebra of a triangle, by this picture which I just showed you, is just the tensor product of the two Skein algebras of the bigons. So this OQ tensor OQ. Now, this is a very simple example, but it can be generalized. And in fact, Tang and I proved that for any surface with non-empty boundary, the SLN Skein algebra of it is going to be a free module, is going to be tensor product of OQs. And each of them has a basis, so consequently, I spelled Kashiwara here in Polish way, Kashiwara-Lusztig basis. In particular, the tensor product of those has a basis, has induced basis. So this is a novel basis for Skein algebras and also for character varieties, at least for surfaces with boundary. In fact, this machinery can be pushed further. So Constantino and Le and Higgins, for any ideal triangulation of a surface, they defined using the splitting theorem, the splitting business, and they defined an embedding of Skein algebras into quantum tori. And one can believe that such embedding exists also for higher n. And this is subject of current research. My collaborator is working on this with his student, I know. And also the issue of basis for sigmas with boundary is a subject of current research.
Sorry, Adam, this is interesting. Could
Yes.
you please make it precise? When you say quantum torus, what's the deformation parameter, and in what sense you're talking about embedding? Could we see some formulas? Because, you know, this is when you use this NCG jargon, it can be confusing. Do you mean embedding
So which quantum torus?
Exactly, yes. Which quantum torus, and are you talking geometrically or algebraically? Do you mean an embedding of an algebra in an algebra, or do you mean an embedding of a quantum subspace in a quantum space? It's, you know, fun.
So the quantum torus will have n variables.
Mm-hmm. And unitaries, yes. Mm-hmm.
And they don't commute, obviously, but they Q commute.
Mm-hmm.
And what?
Mm-hmm.
Okay. They Q commute. So xi, well, xi xj is equal q to certain power, and I will denote this power by, I don't know, d ij qj x.
Where dij is a certain anti-symmetric matrix, right?
Exactly. But now, I guess what, yeah, exactly. So these are entries of anti-symmetric matrix. You can ask me what matrix, but it's a technical question. And
No, I'm happy with the
able...
matrix. I know that it's something that can be figured out. But when you say embedding, I want to see a map. It's a map what? It's a map between algebra.
Yeah. Well, it's an embedding of algebras. Yes, algebra embedding.
Okay.
I don't think I can write. It's not that easy to write the formula right now.
Yeah, but you mean that you take this S and sigma, right? This is what?
Yes.
This is an algebra.
This is algebra. This is Skein algebra can be embedded into quantum torus.
And then here you have. Let me write it down. And here you have just a map into this. Let me call this A. Okay, you have a map here, and this is a homomorphism of algebras, which happens to be injected.
Yes.
Okay, that's what I wanted to make sure.
Yeah, that's.
Thank you.
Sorry, shouldn't be these xi's invertible?
Yeah, they are unitary, right?
No. Unitary doesn't make sense.
That's right. Tomek, you are right. Of course, they should be. I'm not going to write it here, but they should be invertible. Yes.
Just algebraic, so no unitary or non-unitary. But you are saying that the OQFSLN embeds into
yes, in particular
into the torus.
I'm
so capital N equal 1. I have kind of.
Well, actually, Ryszard,
okay, I have problems understanding it. So I have problems believing it. Let's put it this way.
May I notice something? So
yes,
this isomorphism between Sn of sigma and OQ of SLN to some power, tensor power, is an only module isomorphism.
Correct.
Yeah, okay, not as a.
So it's not an algebra embedding.
Yes, but that's important. Yes.
Okay, so let's actually first of all let me.
You said algebra embedding, right?
Yeah, but for Sn, not for the powers of.
But slowly, slow down, Piotrek. You are saying that it's an algebra embedding of Sn sigma. So which algebra structure?
Yes. So in fact, I do claim that OQ will embed into quantum torus.
So you do claim that. Okay.
Yes. And but you know, so frankly, this is not the aspect of the theory which I was so much involved myself. But I do claim that. Are you absolutely sure this is not true?
No, I'm not sure, but I have problems believing it. Let's put it this way.
Yeah,
okay.
I am pretty much sure, even though I'm pretty sure in what I'm saying here. I believe that this is an embedding. You can embed OQ SLN into quantum torus.
Can I ask also? So this means let's take SL2, then you have some number of generators, okay, maybe 4. And then you say that you can find such a number of elements in this non-commutative algebra torus which satisfies the relations you have. Yeah, and moreover, it's injected. That's what you claim.
Okay, so yeah, are you dequantizing the picture? That's what you are doing?
No. Quantizing SLQ2. Let's take the S capital L capital Q2, okay, which is OQ SL2 with coefficients in.
Okay, should I take OQ or should I take
OQ is okay.
Okay, so I'm taking OQ.
Mm-hmm.
But
Ludwig, in terms of generators and relations, right? And
yes,
to the non-commutative torus algebra. So probably it exists. I don't know, but
well, it's not obvious. It's not...
Okay. No, sorry. So for Q root of unity, your quantum torus is more equivalent to a torus.
Mm-hmm.
And I don't
okay,
believe
okay.
you can include OQ
Okay.
SLN into matrices tensor torus. I just don't believe it.
Oh, very good.
Okay, we get to that later. Okay, just continue. Sorry.
By the way, Adam, your time is basically up, so you should think about winding it up.
I see. Okay. Well, good question. I believe it is true, but maybe actually we need to have root of unity here. Sorry for that. I need to look and check. As I said, this is not the aspect of the theory which I was working on personally. All right. Well, I have only 2 slides left, and I maybe just say something very briefly. How much time I have? I guess I have -1 minute.
No, you have 0 minutes.
No, you have no. Piotr, relax. You have time enough for 2 slides. Don't worry.
Of course, I'm not saying he shouldn't say it. I'm saying that he should bear it in mind.
Okay. So, I want to go back to this original definition. So we included here certain relations from the Reshetkin-Turayev functor, but it may look kind of arbitrary what you did here. So I want to convince you that it's actually the result of this construction is not arbitrary. And so there is a more general, abstract, but general construction of Skein algebras, which I can try to tell you about very quickly. So it uses factorization homology, which is certain theory developed by Bellingson and Drinfeld in the setting of conformal fit theory, and then by Lurie and other guys in the topological context. And in a nutshell, it takes an algebraic object called EN algebra, which is an algebra over operate of little disks or little cubes, and it associates any n-dimensional manifold, possibly with boundary, a certain category, which is denoted by this integral. And it turns out that this object for E2 is equivalent to a pivotal braided category, like the representation category of quantum groups. And so in this context, it was studied by these people, Ben-Zvi, Brochier, and Jordan. And so you can ask, what kind of category is that in our context when you take a surface and the representation category of SLN? Well, it turns out that this is a category which is equivalent to the category of left modules over our Skein algebras. So this category, this factorization homology does not have more information than our Skein algebras. For technical reasons, they talk about compact surfaces or surfaces with compact boundary, meaning with loop boundary, and you have to remove, well, this is only true for surfaces with single boundary, which is a loop. And to be precise, you have to remove a base point from the loop to make an ideal point in the boundary, but that's a technicality. This is exactly factorization homology gives precisely category representations over our Skein algebras. And this was already observed by my collaborator with his student Yu and by Korinman for n equal 2. And you may ask, how do you define this object? And well, if I can show you the definition, I have to warn you, it's very abstract, although in some sense also elegant. So let's do it. This is the last slide. And so, you know, if it's too, hopefully we can survive this. So you consider a category of surfaces, and this is an infinity, 1 category. Objects are surfaces with boundary, morphisms are their embeddings, 2 morphisms are isotopies between embeddings, and then there are higher level morphisms, higher level isotopies. And it's a monoidal category with a monoidal structure given by disjoint embeddings. And this category has a full subcategory of disks. And those disks, frankly speaking, may contain partial boundaries like arc in the boundary and their embeddings. All right, so then there is a little lemma, technical lemma, that any pivotal braided category I don't know why it's twice, defines a symmetric monoidal functor from this category surf into certain infinite one category C, whose objects are certain presentable categories. The word presentable is actually quite complicated term, technical term. The construction of this category is quite technical in itself. But then this integral is the left Kan extension of this functor. Which functor is that? This is the functor given by this monoidal functor, by this functor associated with the, in our case, with the representation category of quantum group, of the quantum group. All right, and what does it mean? Well, in more concrete terms, it means that you take certain colimit. So this, okay, this script C is this C. You take certain colimit in this category. What kind of colimit? Well, you consider all possible embeddings of collections of this into a surface, and you take colimit of this functor F induced by, again, representation theory of quantum groups over such embeddings. And it turns out you get category, and the category is exactly the category of modulus over our Skein algebra. All right, so that's much I have to say. There's many topics which I didn't cover, like cluster algebra structures, quantum cluster algebra structures, and others, which are also, maybe I should say that very quickly, those Skein algebras are examples of quantum cluster algebras. Thank you for listening.
Okay, thank you, Adam. Thank you very much.
Thank you.
And let's continue with the questions. Let me start because my question is very simple, Adam. What do you mean by pivotal braided category? Pivotal braided, you had it in.
Pivotal means it has, pivotal means has duality. So it has, for every object V, you have dual object V star, and there is a pairing from.
Okay.
From, yes, and so braided category is pivotal.
Wait, you mean every braided category is pivotal? No.
I believe so, yes. Because, sorry, when I say braided, I mean ribbon category.
Oh, ribbon, okay, okay.
Yes.
Okay, okay. All right, I'm fine, Tomek, go ahead.
Okay, I have a question. I am familiar with the approach of Balog, Kania Bartoszyńska, and others when these people introduced some Poisson structure on the character variety.
Yes.
And this character structure, this Poisson structure is very easily can be defined using some scalar product and some operations on links.
Yeah.
What can you describe this quasi-classical limit when Q tends to 1?
Yeah, very good question. It's a good point to make. So first of all, I should tell you this. So this is for surfaces. Character variety of a surface has a symplectic structure.
Mm-hmm.
The symplectic structure was developed by Atiyah and Goldman, I guess different approaches. And so this is, and for what Bullock, Froman, and Kania Bartoszyńska proved is that this quantization of the SL2 character variety for n equal 2 is in the direction of the Atiyah or Goldman Poisson structure or symplectic structure on the character variety.
Tomek, you muted yourself. Tomek, you muted yourself.
Sorry. Have you computed this Poisson structure, the direction of your infinitesimal deformation in this case?
No, I didn't compute it. I mean, you know, it can be done. It's not clear what form specifically to write it, but yes, it can be done. In fact, so obviously, basically, we have a conjecture. One can create a conjecture that what I just said is true for any n. Yes, it's a very, very reasonable question to ask. And I believe the answer is yes.
Okay, so can I ask next question?
Yes.
To extend the first one, then you can consider formal deformation quantization.
Yes.
Okay.
So for me,
And
this is a formal deformation quantization.
If you take Q being a formal exponent of some infinitesimal parameter h, let's say.
Yes.
As physicists do, then you can take formal power series.
Yes.
And then the coefficients of this Skein quantization of the character variety, at least for SL2, are invariants of finite type.
You mean invariants of finite type in sense of not Fiore?
Yes, yes, precisely. On the other hand, if you think about deformation quantization,
yes,
then you see that up to, according to Kontsevich, every such a class of gauge equivalence of such a deformation is equivalent to a class of equivalence of Poisson structures.
Yes.
So my next question is it anything known about gauge invariance of finite type?
These are very interesting questions. But wait, so first of all,
yeah, in a sense, up to this equivalence, this quantization is unique if you fix this Poisson structure.
Yes. So
and from this deformation, you can obtain some link invariance. But it's known from Kontsevich formality theorem that if you change this quantization into something, then up to some gauge transformation, all these formal series can be deformed into some other formal series with some different coefficients.
Sorry, Tomasz, what are you trying to say?
Sorry?
What are you trying to say? There are non-equivalent deformations.
Yes,
non-gauge equivalent deformations. So what
yes,
I'm trying to say.
But if you fix the Poisson structure, then up to gauge equivalence, you have only one class of gauge equivalent deformation.
No, it depends on the choice of associator. No. No, there is no unique quantization of Poisson structures.
No, this is a theorem of Kontsevich.
No, it's not a theorem. No, Kontsevich showed that there is a quantization. But the Teichmüller group acts on quantizations. There is no unique quantization of Poisson structures. Different procedures give you different quantizations.
I'm not talking about different.
Not gauge equivalent.
I'm not.
And this is not Kontsevich construction. This is not covered by Kontsevich because it's a singular case.
Yeah,
it's not a smooth case.
About singularities here,
right? It's
so
not
there
a
are singularities
case.
here. So,
yes.
so the reason. Okay,
it's not Kontsevich.
Okay, so this variety is in the sense of algebraic geometry with some singularities. It is reduced, by the way, I suppose.
Yeah, sure, but it's singular. So
it's singular. Okay, so this non-equivalence is caused by the singularities. These different classes.
No. Even if you've got a symplectic. No, okay, not symplectic. As soon as you've got a let's say, if you've got singular Poisson structure, there is no unique quantization. Quantizations depend on the choice of associator.
But
Quantization is not unique, period. That's not what Kontsevich says. Quantizations are not unique.
no. In the smooth case, I'm sure that
No, even in smooth case, they are not unique.
No. So
no, because if you choose
why
different
do you
associator,
introduce
you get
this
different quantization?
associator? Because
Quantization depends on associator. Its construction of quantization is the same as choosing an associator. Quantization happens to correspond to a very special associator. But in general, quantization depends on associator.
I'm citing a theorem, so I don't know.
Which is what? Which theorem?
That there is for a smooth Poisson variety, you have an canonical bijection between isomorphism.
No, it's not
classes.
Canonical. Where do you have this canonical from?
But maybe it's not a bijection, but maybe it is canonical construction. That's what you mean for a smooth manifold.
You have a construction, but there's no canonical.
No. I'm not talking about this Kontsevich construction. I'm talking about the theorem that the isomorphism classes of Poisson structure corresponds to gauge equivalence class of deformation quantizations.
Yeah, but it's not canonical. It's not canonical.
In any event, I'm afraid I don't have much to say in this context. Because,
but Richard and Tomek, let's focus on questions to the speaker, not discussion between you.
Okay, so my question was, if you change this deformation quantization with the same Poisson structure.
But I wouldn't know how to change it, frankly. I'm happy I have one theory. I wouldn't know how to quantize it differently.
You can, for instance, you can apply gauge equivalence. So there's always way to deform this deformation quantization by twisting by this gauge. So
I'm not familiar with this.
Okay. Okay. Anyway, if you have this Poisson structure, then you for at least for SL2C, SLQ2C. Okay, you obtain this invariance of finite type.
Okay.
Which are equivalent to this deformation quantization.
So,
because they are Taylor coefficients in a sense.
Frankly, I'm a little bit confused, and it's my fault. I know when you say it's a finite type invariance, because those invariants. Okay, we're going to talk about. So you have to take link in thickened surface, and you can associate to it certain algebraic object, and then you say that link in thickened surface is a manifestation of a virtual link. That's what you are saying. No, wait. Okay, so the finite type invariance of links in surfaces. Yes. Okay.
Thickened surfaces. Yes.
Yes. Well, I strongly believe that the same is true for NAN, but it wasn't investigated. But I don't know how to connect this to changing of the deformation. How to connect what we're discussing now, finite type invariance, to changing of deformation.
So the Skein quantization is, of course, is distinguished from the point of view of link theory, of link invariance. But I wonder how unique it is from the point of view of representations of SLQ2C, let's say.
I don't know. Yeah. So now I think you are asking about classification of deformations of character variety, and
maybe it's too much. Maybe it's too much.
I don't know.
A little bit deform the situation.
You know, I have one deformation, and I'm still.
Yes,
still
I know.
Very difficult for me, but yeah, it's hard. And of course, the question is, I mean, there could be other deformations. It's not clear how much mileage they will give us. I mean, this one has rich fiore. You know, it's connected to Atiyah bot, to Goldman. Other ones, I wouldn't know what to say about them.
Yeah. So I was asking about this Poisson structure, but then to deform this Poisson structure to an associative algebra, you can have different procedures. For instance, Kontsevich used very specific representative of this class of equivalent.
Well, it would be very interesting to see if Kontsevich's procedure
how is it related to the Skein relations?
Yes.
Yeah.
I don't know. Do you know? I mean, I don't know about this. I mean, but
I tried to do something, but I lost my grip on.
No. Sorry, Kontsevich procedure has nothing to do with it. It's so. The Skein relations. So you choose your, well, I don't know, your group, right? Your simple compactly group. So given that one, you can construct your Skein algebra. Actually, Mogen, so the point is that Skein algebra and Skein modules, they don't really depend on Q. All of it have its coefficients, Laurent series in Q.
But Skein relations depend on Q, of course.
Yeah, but as Laurent, as coefficients Laurent polynomials in Q. Okay, it has nothing to do with quantization in this sense, on the nose of it. But then you can reconstruct Kazdan-Lushty quantization of UQ. Okay, so it's kind of relation. No, actually wrong. So as a matter of fact, so somehow your Skein algebra depends on the choice of quantization of Kazdan-Lushty. Actually, Kazdan-netting of quantization of UQ.
Richard, can you repeat your claim? So
what I'm saying is that so you write down your Skein algebra, right? Relations.
Yes.
It's easy. I just write them down. That's kind of straightforward, right?
This what? Sorry.
It's more or less straightforward what you write down here, right? There is no in some sense there's no quantization involved. In some sense, what you got is kind of a module. So all you have are vector spaces over Laurent series in Q, right?
Yes.
There's no quantization, anything.
Yeah. Well, there's certain module quantization, but I know you wouldn't call it quantization.
Well, no, you don't really have. No, you don't really have quantization. You have some modules over Q, but when you want, what's the word? Let me think a second how to say it. So that's why I was saying root of Q has nothing to do with being root of unity. Right here.
Nothing.
Not really. It's really just
Q is a
formal parameter.
Yeah.
It's variable, right? It's really it's actually formal variable. It's Laurent series.
Yeah.
Q, right?
That's right.
That's what's happening, right? And that's but the construction itself depends actually on Kazdan-netting of quantization of UQ, the formulas themselves. If you choose different quantization of UG, the formulas would be slightly different.
I see.
Okay, you might get different formulas.
Oh, okay.
Not the ones you have, right? So in general, you just have your basically a modular tensor category as your coefficients, and use that one to construct a Skein algebra.
Okay. Yes,
and
I
Skein
agree.
modules and invariants and so on.
I agree with you, and it would be interesting to consider those. So I don't know if so they are essentially different quantizations of the enveloping algebra. Then you say?
Oh yeah, sure. Which are not equivalent.
Non-equivalent.
Not gauge equivalent.
Not. Oh, I see. Okay. Yeah, it would be interesting to consider this theory for them.
And so I think the one. I think that Koncevich's one, if I'm not mistaken, that's the one which has rational coefficients. But in general, you don't have even rational coefficients.
I see.
So, and they are really not they are really not gauge equivalent.
I see. Okay, that's interesting.
And the invariants depend on the choice, on this kind of choice. Okay, there is a reason I do have some kind of background, because now you are talking about 2005. I got a paper with friends of mine in 1992, 93, where we constructed TQFTs from 6J symbols. General construction, right? So
yeah.
I've got a quarter century on you.
I see.
In this respect.
Okay. This is TQFT based on what group?
No, not a group. You just it's 6J symbols. So all you need is the decomposition. You need a tensor category, finite tensor category, with a decomposition of a tensor products. Satisfy some. So
okay.
It's a generalized version of Klebs-Korn coefficients.
Oh, okay. Well, good to know.
That's all you need, right?
I will check it out. Yes.
Yeah, sure.
Okay.
So you need certain structures on Klebs-Korn coefficients. Not just the it's not the classical group, because you want a finite tensor category.
Yeah.
Because you really want invariant, so you want to write down state sums.
Yeah.
Okay, so you really have TQFT. So you have your scalar products.
Yeah.
And there's of course there are all these things. So there's a version. We didn't think in these terms, but there's a version of twist, which simply, in the simplest cases, comes from the fact that square of Fourier transform is not 1, but -1.
Yeah.
Right. That's what happens for SU2.
I see.
That's where the twist comes from. Really. I'm
going to check it out then. And to relate this maybe, so yeah, you mentioned TQFT, and I also mentioned TQFT, and so you can also consider this theory over kth root of unity, or maybe n plus kth root of unity, and the certain quotient of the Skein module for a surface, Skein algebra for surface, certain quotient of it will give you the TQFT observables space for the surface. So you can go from this construction to Reshetkin-Ture of TQFT.
Yeah, sure. Yeah.
And by the way, now I remember, yes, of course, for the quantum torus embedding, we need to have roots of unity. Yes, so yes.
Well, otherwise it doesn't make much sense, but
yeah.
Even there I'm a bit no, that's okay, because at the roots of unity you have finite your representations are finite dimensional matrices. So yes, you can map them into and torus at roots of unity is just a bundle of matrices.
Yeah.
So you can embed them this way.
And this all becomes then a how this is called polynomial identity algebras. This becomes subject of polynomial identity.
Okay.
So you see, Adam, you turned Richard into a believer.
Kind of, yes.
That's good. Any further discussion, or should we wind it up? Anybody, any further questions, complaints, comments, suggestions?
No complaints whatsoever, but it's getting late-ish, yes.
Yeah.
For us, it's getting late-ish.
Okay, so
maybe I would have one question more.
Yeah.
So if you related already this Skein quantization with this Kardan-Lustig representations, theoretical deformations, what is the relationship between these strands, these braids, with a representation theory of in Kazdan-Lustig theory.
When you say these braids, which ones you mean? The
So
ones.
there are these generators in this gray.
I think my sharing is paused. Maybe I can. Let me try.
You cannot see. Sorry.
Or,
you cannot see my cursor, of course. Sorry. So you have these generators.
Yes.
Okay, which are related by these relations. So what's the correspondence between these generators and this Kazdan-Lustig theory?
Well, okay, so I wouldn't call them I'm not sure. I mean, these are
there are local modifications, okay, because local,
Well, as you can see here, I mean, you can think of it as these are certain relations from the Hecke algebra, associated with the the quantum group UQ, and so I guess different deformations of USLN will have corresponding Hecke algebras. But frankly, I am a classical kind of guy. For me, this is already advanced. I don't know about those exotic deformations, so I don't know how would they look.
Just representation of Hecke algebra. So it's the representation of a braid group in Hecke algebra. That's all.
Yeah.
So therefore, I call them braids, but I meant
they are braids.
Yes.
Yeah. They are braids. Sure. They are braids. But they are here's a representation of Hecke algebra. The representation of a braid group in the Hecke algebra.
Yes. So this was what you meant about this when you meant this this relation between Kazdan-Lustig and this representation.
Atomic, are you asking
I would
me
like to be sure.
Who are you asking, Thomas?
My question is it true that the passage from this Kazdan-Lustig theory to these Skein relations go through this identification of the representation of Hecke algebra, which is related to representations of braids?
Oh, okay.
Yes.
So when you
sorry,
okay.
Adam, it's your
no, go ahead. Well, for me, I use very little actually Kazdan-Lustig. I only, I use Drinfeld Jimbo quantum groups and the theory
standard quantization.
Yeah. So I guess you're asking still about non-standard quantizations, yes?
Maybe, I'm not sure.
If it's not standard, it goes.
My
to the
intention
child.
was to make clear relation in the standard case. But if you say that my question suggests that I'm thinking about something non-standard, that maybe, but this only means that I'm confused. Okay.
No, it is standard case. So Kazdan-Lustig quantization, right? No, actually Kazdan-Etting of quantization. So there are these Lustig generators of a braid algebra, which are so these are representations of its braid algebra. In the algebra, well, kind of version of Hecke algebra of Laurent series in Q. So this is really representation of Lustig generators.
Okay.
As they are. Okay.
Standard. Everything is standard.
Whatever standard means.
Okay.
I don't know. I don't know what standard means, right? If you say standard, but if you leave the SLN to SLQN, then your Coxeter group leads to the generators, lead to the braid generators, yes, and standard.
Okay, good. Thank you very much.
Sure.
Gentlemen, I wish I was there with you guys in Warsaw.
Actually,
it
would be much better if we could talk, right, directly, instead of the stupid thing.
But then, unfortunately, I have to wrap it up. in a
Okay,
moment.
so let's thank Adam again. Okay, thank you so much
Thank you very much.
for an inspiring talk. And
thank you for
by the amount
very-
of discussion, you see that we were paying attention to what you were saying. So thanks again. Let me stop recording.